everybody knows. Everybody knows about smell of coffee, but you also now know about smell of onions. Good. So, physics perspective meets engineer right here, where engineer says that the resistance to the body, which is definitely eventually due to molecular motion, that's a source of irreversibility. So physicists interested in the symmetry, he say, look, without any molecules, without any viscosity, it's irreversible, right? T2 minus T. Anytime I see drag, it's irreversible. So I see drag which depends eventually on the existence of viscosity, but it's independent of the viscosity magnitude, right? So physicists are interested in symmetries, broken symmetries, and particularly in conservation law, right? And here they meet engineer where they discuss how the hell you need to spend half of our gas, which we and oil, just to burn to transport this gas, for thousands of kilometers through the pipelines, because of this resistance, which eventually is independent on the viscosity of this, right? And so this is a physics perspective. And then mathematicians come. And again, for mathematics, there are always two sources here. There are two perspectives. There are more, but basically, one is mathematician who came from statistics, and they're interested in this as an example of a very random things with very interesting statistical properties. Incidentally, that's what brought Kolmogorov to it. He built an axiomatic theory of probability, and he was working more or less with scalar random quantities. And then at some point he thought, well, I need a vector random quantity, something vector field which would be random. What is it? It's a turbulent flow. It's a vector field which randomly changes. What helped also that he was very young and ambitious, and they were actually looking for a person who would be doing some kind of, who would be a great mathematician, but doing some kind of a practical meteorological and different things, and that's what immediately opened for him a possibility to be elected academy member and all this. It helps, I mean, this, such motivation from real life. So first of all, it's statistics, but second is ODE, PDE. Because for mathematician, and that's what you see, for example, at the college lectures, that you are really interested what kind of solution differential equation can have. And when you look from ODE perspective, ordinary differential equation, it's essentially you're doing Lagrangian. You're looking for a given fluid particle, O2, O3, how they move, right? In a given flow, like for passive scalars, they are described by ordinary differential equation, which could have a very non-trivial property. You can have smooth flow, which provides you zero Lyapunov exponent, dynamical chaos, mixing, and now you come back to engineers and explain to them why the hell you can only predict weather for a week. You know why? Never trust any 10-day forecast. Week forecast. So where is this 1 week comes? Yeah?
The time a small perturbation takes to get to the large scale.
But why it's 1 week?
Well, it's how the system is.
Well, you are, weatherman comes to you and say, explain to me, you're a physicist, you know to do simple estimates, right? Like Fermi said, you can estimate everything, just think more than 2 seconds. So where does this 1 week come from? Huh? Yes, but why 1 week? Not 2 weeks, not 1 day. Well, it's Lyapunov exponent. Okay, so why Lyapunov exponent is 1 over 1 week? Estimated. We all know what is Lyapunov exponent. Let's not explain to each other what is Lyapunov exponent. Give me an estimate. So what? You take height of the atmosphere, which is 10 kilometers. Okay. So anyway, any time is distance divided by velocity, right? Guys, I mean, let's just, imagine that you have, somebody comes to me and ready, or to you and ready to pay you for consulting like $1,000, just give him a right estimate. It immediately stimulates your mind, right? Here is so L over V, right? This would be time. What is L? You suggest 10 kilometers. What is V? 10 meters per second. That's 1 day. It's an Earth size, more or less, or half Earth, divided by a typical wind speed, which is basically like 20, 30 if you go for atmosphere. So it's the size of the, I don't know, size of Europe divided by a typical wind, that's 1 week, okay? That's it. I mean, fluid mechanics is a simple science. It's distance divided by velocity. So that's where these people talk to these people, but then they study partial differential equation, and then they find out, whether you've seen it at Vicor's lectures, that this equation can have a very non-trivial solution, that can have a solution which are weak solution. Which means that they kind of have something non-smoothness in them. And then they discover that this non-smoothness over here somehow talks to this anomaly over there, that the moment that you have a non-smooth velocity, and it's non-Lipschitz, for example, you don't have a single trajectory, you can have trajectory splitting or gluing. And that immediately breaks conservation laws, okay? And so that's how all these three approaches talking to each other, okay? And now, with all this general introduction, I want to continue and show you in particularly how we are talking to each other. So let's now get back to where we stopped last time. And as we say, and again, I'm here. It does not mean that I'm in between these two people. They sometimes talk to each other very happily without any physicist in between, right? But physicists pretend that we're at the center of the world, like we can talk to everyone. Okay, so what I now want to go back to where we stopped, and we say that this is cascade, and this cascade essentially, I write it for Burgers. You remember that for Burgers we get it d dx 2 u1 minus u2 cube 1 over 3 mean value equal to minus 4 epsilon, and I did not derive it for n-dimensional case. I mean, Berenger derived it, but let me just give you this form. So again, now is you write delta v, it's a vector, and delta v is a module, and it's the same minus 4 epsilon. So this is Kolmogorov 4/5 law, but kind of written in this form, which essentially tells you that some third moment is proportional to r in the first power and gun your smoothness, right? We still don't know what are the properties of our delta v. It's only third moment. But what we do know, that delta v could not be proportional to r when r goes to 0, which would be Lipschitz, right? So we immediately understand that we now don't have a uniqueness of solution. And that's precisely what, you remember any course in mathematics about differential equation. First thing they ask, prove that solution exists and it's unique. Now we can guarantee it's non-unique, okay? What does it mean? For example, for Burgers, again, this law is satisfied with this R12 is much larger, so some new related distance. So in a sense, it's taking the limit nu going to 0 by our viscosity. If you look at Burgers' equation, in the limit viscosity goes to 0, it's a very simple equation, right? That's Burgers' equation, right? It's just free-flowing particles, if there are no extra forces. What it describes characteristics crossing. Let's say if you take u as a function of x, something like this, and then you look at x t plane, what you're guaranteed that the particle which starts at time equal to 0 at this x, let me take it t, so the x would be projected on this. So I'm at this x, right? And this particle would fly with this velocity. That's it. That's what it does. What that particle would do, which starts here, it would fly with higher velocity, which what means? It means that it would go like this. Bingo. What you have? You have crossing of characteristics. That's where shock is created. So you know what happens to this profile. After some time, it would create a shock. And this is after some. This is t equal to 0. This is some later time. Okay. Now what we see is how we create a non-smooth field. You see. And then we understand that, of course, it's a dissipative structure, and it has this dissipative anomaly. Because as we discussed, what happens at the front of a shock, you have one particle moving with a velocity v, and another particle having velocity 0. Right? After this particle hits it, and they now go together with a velocity v over 2, but there are now two particles. You know, I'm trying to be as elementary as possible. That's what essentially one-dimensional shock does. Because you remember that shock was this structure. This was 2w, and that moved with w. So particle with this velocity hit, and then... So now we understand what's going on. This equation conserves momentum. Well, every particle moves with the same momentum. It conserves momentum even with viscosity. Viscosity is just a redistribution of momentum. So we had momentum mv. We have momentum m times 0. We have now 2m times v over 2, the same momentum. What happened to kinetic energy of the particles? We had mv squared over 2. Now we have 2m v over 2 squared. Right? Every such collision, you lose half of energy. When you go into quantum field theory, they like to tell you that behind every anomaly, there are always two symmetries colliding, and one gives way to another. This is the simplest example. You don't need to go into quantum anomalies to understand how anomaly, namely the rate of dissipation independent on the viscosity, which makes it all possible, means that you have a momentum conservation and energy conservation. You cannot satisfy both. One needs to give way. Momentum survives, energy not. You look at Dirac fermions and they say, okay, here is axial current conservation, here is the charge conservation. You cannot have both when you have in a quantum state, blah, 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 all this. But this is where it comes from, 18th century, well, 19th century. By the way, Burgers did quantum mechanics, and like everybody did quantum mechanics, and then a position opened in Netherlands for fluid mechanics chair. And he went into fluid mechanics, again, how career choices. So this is something which tells you how non-smoothness, non-uniqueness of trajectory, and non-conservation are related. Okay? Good. Now, I want to consider with my physics and remind you what we ended last lecture and go into other symmetries. This is a breakdown of time reversibility and finite energy dissipation. But we started to discuss the probability of velocity difference at a distance r, right? And we say that this probability distribution does not have time reversibility, which means v to minus v. It's a time reversal, it's just v to minus v. Because we have this moment delta v cube proportional to epsilon r, and any odd moment means that you lost time reversibility, right? And then we discussed, does it have self-similarity? So what I'm now doing, I'm taking all this flux dissipation stuff and trying to push it further, thinking about whether the breakdown of this symmetry of reversibility means that some other symmetries also broken. What would self-similarity mean? Self-similarity mean, if you're experimentalist, a huge benefit. So instead of measuring one function of two variables, what you really need, well, dimensionally it's 1 over delta v, right? Because the integral of over delta v is unity. So you say that there is some function of their combination, right? That's self-similarity. Anytime you find self-similarity, it means that you now need to measure only, on a line, not on a plane of your parameters. This, by the way, Maxwell was an editor of Reynolds' paper, and looking at all this data which Reynolds collected, he said, why don't you look at the self-similar variables? So even though we always say that in fluid mechanics we have it from Reynolds, Reynolds got it from Maxwell. Well, of course, Reynolds got this data, and also he actually had it there. It just was very messy. And Maxwell kind of made it somewhat neat. So now, if this was true, and this was true, this would be 1/3, right? And that would mean that if you look at any moment, that would be estimated as epsilon r in the power n over 3. And we know that it's not true, right? Or somebody doesn't know it. How it's evidently not true? For example, for burgers. Somebody come to you and say, look, for burgers we know that the third moment of velocity difference is minus 12 times epsilon times x. So is the second moment of velocity difference in burgers equal to epsilon x in the power, epsilon x12 in the power 2/3, or it's not? You know how to answer this? By passing n to infinity, we immediately know that it's wrong. For burgers, fortunately, we more or less know what's going on because of this kind of a simple picture. So if we would create some kind of a large-scale forcing which produces such, size L modulation in your velocity, we know what happens to each such modulation. It's negative front making sharper because this particle moves faster than this, so they catch up with them. And this particle moves slower, so it goes into this form. So now, if I look at this form and I try to estimate what is delta V in the power n, okay, I would immediately see that there are two contributions possible because essentially my flow is a set of smooth parts and shocks, right? So what I would say here, that such smooth part, if my interval x12, this is my x12 interval, happen to be on this smooth part, which is with overwhelming probability would happen, right? With overwhelming probability, I would have it there, and it would give me Rx burgers. It would give me x12 in the power n, because it's a smooth part. Is what we always wanted for Lipschitz, right? Now, but there is another contribution, and this contribution happened when your interval, this is 1, this is 2, such so that shocks is over there, right? And now the contribution here is independent on this size. As long as shock is inside, and we again consider the limit with x12 is larger than the viscous related scale, which is the width of this shock. So this contribution is independent of the length of this interval, right? Because it's essentially just RMS, let's call it URMS in the power n, because this is n. But there is a probability to get shock inside my interval which depends on the length of this interval. And how it depends? How the probability to get a shock inside some interval depends on the length of this interval. Huh? 1 over the... I'm not asking about that. I'm asking about the length. How the probability of shock depends on x12. I make my interval twice larger. What is the probability will be? Twice larger. Good, okay. So what we now conclude is that this would give you x12. This would give you something dimensional. I don't want to even bother with it. So you see what is called sometimes on a jargon of Burger's people bifractality. It tells you that whatever moment you compute, because physics is so simple, essentially your acoustic turbulence, and this is something which is not imaginary. I had a friend, and in the basement of it was Naval Graduate School in California, where they train naval officer, but they were actually some naval officer were doing graduate degree in physics, so they had this big pipe where they have loudspeakers, like 40 meters. And it created more or less one-dimensional noise which ran in one direction along the pipe and were perfectly described by Burgers and did all the statistical measurements. So what we now conclude is that when n is less than unity, which term wins? This or that? If you look here, what stands here is URMS divided by L is a typical derivative slope, right? The power n. So when n less than unity, you think that this term wins, but it's proportional to the first power of x. And this is proportional to the power which is less than unity. And we consider limit not only x12 much larger than O of nu, but much smaller than L. This L is a large thing, and this is small, right? So when you consider n less than unity, this is the main contribution. Because in the limit, when x12 very, very small, it's proportional to a larger thing than this one, right? And when n larger than unity, you have this term, of course, much, much smaller because you have this L in the power n, right? So what you conclude that if you say that this is proportional to x12 in some power zeta n, and this zeta depends on n, then you can plot zeta, zeta as a n. First of all, for 3, it's always unity. For Burgers, for Navier-Stokes, for many other situations, right? So it always passes through this point. Third moment has a scaling which is equal to unity. But for Burgers, we find out that there is 1, 2, and the curve goes like this. Which immediately tells you that this is not self-similar. It's self-similar only in the case where this exponent like this, right? When we initially say that if it's like this, then delta V n is epsilon n over 3. That's Burgers. What about Navier-Stokes? In Burgers, we kind of derived this hand-wavingly, but there are actually more nice way to derive it. And then for Navier-Stokes, we go and we measure. It must start from here, that's for sure, right? Delta V in the power 0, it's unity, average of unity is unity, it does not depend on the distance, so the exponent is 0. It passes through this point. How it goes? Yes? From Kolmogorov, 41. You would expect, Kolmogorov lived long life until 87, and he was born in 1904. So this was Kolmogorov 41, but he lived long enough until 62 at least, so that he actually derived that this must be some kind of a convex curve passing like this. And at his time, we measured it until, I don't know, like, imagine this is a login. So this is like 8, 12, infinity, right? But just a couple of weeks ago, there was a pretty recent, very good data by Srinivasan and Bruria, and there are two interesting aspects of it. First of all, that for three-dimensional turbulence, it's important whether you look at this as this is a vector now. Delta V is a vector, so you can look at longitudinal or transversal velocity difference. They have different scaling, but the net kind of statement is that it's saturates. Well, really, it's very, very close to it. For here at 2, the difference is few percent. At this point, engineer would say, okay, guys, who would care about few percent difference? I remember when with Uriel Frisch and some other people, we were nominated for some kind of big prize, and we were needed to kind of write some short explanation why all this anomaly. Actually, it was all about this curve, right? And why it's important that we had a difficulty arguing this tiny difference. Somehow, great people of Europe need to be so excited to give us that much money for this like few percent. As they did not, by the way, and I think that they were right. But for physicists, it's huge. Because it tells you the following thing. So if you now look at delta V squared, dimensionally, it's epsilon r to third. You remember, when you Fourier transform it, you would get k minus 5 third, which is, as I say, the most widely known incorrect result about turbulence. But then what it actually tells you this, that there must be some other power of r, and it's usually called delta. So zeta n minus n over 3, it's called delta n, following quantum field theory, where it's called anomalous dimension. So it's a scaling exponent, kind of natural to call dimension. What is important that it's positive here and it's negative here. So here is your delta 2, and here is your delta 4. So what it tells you that if it's like this, then it must be dimensionless, right? What must be the scale which stands here in the power delta 2? What is this scale? There are two scales in turbulence, pumping and dissipation, right? So what we're now asking, if the scale invariance broken, that means that you aren't self-similar. You rescale it, make it smaller, and it's not the same. But it's not the same in a sense that you're closer to the viscous scale, or in a sense that you're farther away from a pumping scale. So every time you see breakdown of scale invariance, it tells me that your system remembers the beginning or knows about the end, right? And in quantum field theory, it's usually ultraviolet divergences and the memory of a small scale where all this your physics originated. Because all our quantum field theory are effective theories. You go start from small scales, you go to larger and larger scales. But in turbulence, it's a cascade. And this is particularly a direct cascade so far, right? So we start from large scale and we go down. And the number of steps of the cascade, this is what is remembered. Like in the morning lecture, you've seen this. You may try to attempt this cascade process at a similar process. Well, it's not. A little bit, but it's not. So it's L. It tells something which, as an engineer, you may not care because our planet is small enough to care. But as a physicist, you say, oh. And why you do it? Let's keep epsilon fixed. Namely, I have a cascade, and through a given scale R passes Z amount. You remember this pipe? Cascade is a pipe by which your energy goes to larger and larger wave numbers, smaller and smaller scales. Let's keep it. Which means that we also keep a third moment. Third moment is epsilon R. R is fixed, epsilon is fixed, third moment is fixed. What happened to the second moment, which is a spectral density of turbulence when L goes to infinity? Okay? So you remember in K space, this is this cascade, but now I take this 1 over L starting wave number and just turn it to 0. Or in other terms, I'm turning the size of my box or scale of my forcing to infinity. What happens? Look at this formula. Well, it's in the denominator, and delta is positive. Don't be afraid to say it. What happens to the spectral density of turbulence if at a given scale R, I keep the flux epsilon, but I increase the size of the scale of the forcing? My Stanislavski pose worked. It goes to 0. You, Berenger, me, we get used to it. 40 years ago, when I first met Krajknan, I did not believe it. I said, it's impossible. And now I'm convinced. So sometimes I forget how unbelievably strange it is and what it tells us about turbulence. It tells us that in a very, very large box, you can keep that flux, that rate of dissipation, with almost no turbulence intensity. Delta U squared, it's an energy. That's an energy. That's a flux. Okay? What physically it tells us? It tells us that the statistics of turbulence is very much opposite to whatever we learned in our first statistical courses, where we mostly were dealing with Gaussian, Poisson, binomial, and such distribution. It tells us that the statistics is extremely intermittent. There are very, very strong fluctuations which happen very, very rarely. But as you increase the size of your box, and you want to keep the same flux, those more and more rare and more strong fluctuation would keep this flux, would provide your dissipation, right? And the rest would go to 0. You see, that's why all this is positive, means this goes to 0. All the higher moment, on the other hand, if you look now of, no, I don't want, I want to keep it. So let's erase mathematicians. Sorry, Vlad. You'll be back. So if you now look at delta V4, it is epsilon r 4 over 3 r over L delta 4, but this is negative. So it's essentially L over R in some positive power, which tells you that, and it's exactly a sign that your probability distribution have very fat tails. All the high moments are actually very large, but your second moment is actually very small. And of course, it's quite of trivial to understand it looking at burgers, right? When you look at burgers, you say, okay, what is actually my energy dissipation rate? And my energy dissipation rate is always is kind of some U cubed divided on L, right? So if you want to keep your, and this is your epsilon, right? So you want to keep this, and your L goes to infinity, it means that your U, your RMS, as we denoted, this is your RMS, it scales like epsilon L 2/3, 1/3, right? So if you'll be interested in U squared, and you'll be interested in dividing it by L, namely in the density of your energy, because you increase interval. That's how you increase your RMS velocity. So you take your RMS velocity squared, divide by L. But this would give you L 2/3, and this would give you L. And that's precisely, I mean, this is my anomalous dimension for burgers, which is in this particular case equal to 1, right? So you see that this anomalous scaling physically means intermittency. Physically means that in such systems, even though you know the flux, it does not tell you much about other moments. And in particularly, this small difference, or not so small for burgers, is something which has a very dramatic physical consequences. Okay? And another name for this is called anomalous scaling. So where these delta n's aren't, okay? Questions? Everything is clear? So what I did, why you don't ask questions? Everything is clear, or you totally do not understand the word what I am saying? Huh? Yes. Yeah. Well, I assume that, or taking a snapshot of some kind of a decaying turbulence, or you may assume that you have forcing, which forces, let's say, acoustic waves of a wavelength L, right? Then what I know, that for such a wavelength on a size L, there will be one shock, right? And then another L, there will be another shock. So in a sense, when my L increases, my shocks are getting more and more dilute, right? If I want to keep the same rate of dissipation, I need to increase the amplitude of these shocks, but only as a 1/3 power of this wavelength, right? So my energy of every such wave would grow like L in the 2/3 power. But energy density, you need to divide by L. It goes down with L. See, this is a simple picture of anomalous scaling in projection on burgers, which look trivial and still has the same meaning, that as you increase your scale, these events where all dissipation happens are getting more and more rare. But it's enough to carry the flux, right? Okay, so this is what is this small loss of self-similarity, right? Self-similarity would be in a straight line. So what we're now discussing, yes? No, only those with n less than 3. Those with n larger than 3 would go to infinity. That's the point. You see, this is above this line, and this is below this line. So all the moments higher than 3 would go to infinity. They have L in positive power. Okay? That's something which really tells you how strongly fluctuating your system is. The high moments increase, low moments decrease. Question? Guys, you have question? Ask it. Let other benefit. You don't understand something, ask questions. You do community service when you ask questions, because everybody sits and thinks, maybe I am only the stupid person here and everybody else understand. When you ask questions, you immensely help each other, because you know, wow, not only me, nobody understands it, okay? Question? No question. Okay. So you want to discuss something else, you discuss it out there. You want to discuss something here, discuss it with all of us. Right? You learn from each other no less than from me. That's important. Yeah. I just did. You want to know what is the true form of the statistical work, but first of all, it's not universal, right? It depending on the forcing statistics, because it has this non-universal part which is related to RMS, right? But then again, it always had a finite variance when you have a finite L. But when your L, it actually is a statement what is the behavior when L goes to infinity. You say my third moment stays constant, then my second moment behaves like 1 over L in the power 1/3. That's it. Which means that you create longer and longer shock, and when you divide by this length, the average variance goes to 0. Okay? This is a very simple statement. You say that you have something like this. This is L 1/3. This is L. This is U, right? So what is your U variance? Is this squared? It's L 2/3. What is your mean variance? You divide by L, right? It's a density of energy which goes to 0, right? Okay, good. So now,
Can we repeat the reasoning in another way by keeping constant the variance? I'm thinking of
no, I was keeping constant flux.
yeah, but can we just try to think if we
If you keep a
the
variance but increase L, then your flux would go up. Yeah. If the same turbulence in a larger and larger box with the same level of turbulence, the same spectral density, would transport more and more, because in a larger and larger box there will be more and more this rare fluctuation, etc. Now, we do know that for Burgers this is 1. And this 1, you remember where it comes from? That the probability of shock was proportional to x12 in the first power. That's this unity. As sometimes, as mathematicians would say, it's a codimension of my singularity in my space. Right? So I have a one-dimensional space, and my singularity are points, right? Shocks, right? On the line. And the codimension was 1 minus 0. So what experiments show about Navier-Stokes? I always knew it, and now they really can see it. It's close, when you go too far enough, as only Srinivasan can do, it gives you 2. What it tells us? What are the singular objects? First of all, if it saturates, it means that this type of structure that you see corresponds to a finite jump of velocity, because you're measuring delta V, right? So, but codimension 2 in 3-dimensional space, what does it mean? Means that the probability to observe it on a scale R12, probability, whatever singularity I have in Navier-Stokes, which would be a velocity jump, is R12 squared, which is area. what I'm saying is the following. I'm now giving you, without any argument, I just go and look at archive paper like 3 weeks ago, that delta V in the power 12 behave like R12 in the power very close to 2. And delta V in the power 14, or actually 13, you can take a modulus, also behave as R12 in the power close to 2, 2.0 something, right? Which means that this curve saturates at large n, and this level at which it saturates is a power which tells you this is the probability that some singular event happened within this interval, and it's proportional to the area, which tells you that this singular event in three-dimensional space is what? Line, exactly. Line. So if you take an area, right, and then what is a point object with respect to area is a line. It's probably vortex line, some kind of vortex filaments. Again, because now I am totally hypothetical. Nobody ever derived it. I actually many years trying to derive this asymptotics in infinite dimensional space, which is, I believe that, but again, I'm very far from really deriving it. But what this data hint is that if the codimension is 2, it means that in three-dimensional space we have lines which are very singular object. Close to this line, the velocity difference on different sides of this line are very large, like velocity difference in a shock, right? Okay. Yes. This is for transversal. Yeah. And also when you do Lagrangian, you can do velocity of a particle, but consider velocity difference at different instance of time. Then Lagrangian corresponds to transversal. Because essentially that's what happens, right? And of course we suspect that those are filaments. But I think it's actually Kelvin-Gauss instability of tangential discontinuity. You know, in viscid limit, it's very easy to produce tangential discontinuity, but it's unstable. It's Kelvin-Gauss instability. It produces such modulation which turns into spiral. And these spirals are probably these filaments, but nobody was ever able to describe it. Okay? Yes?
Could you again say why the 2 is related then to a line and to like a filament?
I'm saying I have a singular object. Okay? If on a line probability of having this object is proportional to the length of the interval, then I assume that this object is point object. Probability of having point on an interval proportional to the length of this interval. Okay? Now, if I'm saying that the probability of having my object in three-dimensional, in two-dimensional space is proportional to the area of it, it's again a point. So the probability of something is proportional to the area in 2D. It means that this something is a point. Probability to find a point proportional to the area. But I'm in 3D. So what is a point in 2D? In 3D is a line in this direction. Okay? So your codimension means that you take dimensionality of space minus dimensionality of your object. For Burgers, this is 1, this is 0. For Navier-Stokes, this is 3. And if codimension is 2, then this is 1. So this is the dimension of my object. So it's a line. You understand this argument? Yes.
Could we imagine those lines to be like vorticity filaments?
It probably, most likely vorticity filaments, but they are vorticity filaments of a very unusual nature. They produce such a huge velocity difference on their both sides. They are very intense velocity filaments, which, like a shock wave, if you think about Burger's shock, it has a jump of velocity of order RMS. Namely, the largest velocity in the system is what you have on the. So those filaments, being very tiny, namely, we are in the inertial interval, and they are smaller, which means they are kind of a viscous-related scale. And yet they produce such a huge vorticity, so the velocity difference on both sides of them are of order of RMS. I think they are a result of spirals out of Helmholtz. I don't know, we'll try to, it's unbelievably difficult to do any analytics about it, and hand waving you can do as much as you wish. So the real people here are people who measure it, yes.
But do they have this result numerically?
Yes.
Are they not able to observe such filaments in those numericals?
They are statistical results. They analyze huge massive of statistical data. Then, of course, you may try to do conditional things and see what actually gives a contribution into this very high moments, and they are working on it. But more or less, you know, the moment that you see something close to 2, it's a line.
They're at very high wavelength?
Well, numerically, yes. It's state of the art. I don't remember now the data, but I mean, this is, by the way, of course, as everything, this is done by this PhD student at NYU. I don't know, you may know him. Yeah? Okay, so good.
One question, sorry.
Yes. Yeah, ask questions. I really want
Is
feed.
it also related to the fact that potential flow-up in 3D Euler is constrained by vorticity flow-up? That's why I was asking what vorticity filament is.
Ask mathematician here. You know, that's that's people who understand much better. But I mean, I think that it's really first of all, I always believe that it saturates, right? And in a sense, that's why I wanted always to do theory in infinite dimensional space. And maybe some of you at some day does, because in infinite dimensional space, the incompressibility is really unimportant, because incompressibility is give v equal to 0. It's one condition imposed on d components, where d is dimensionality. So it's like when you go to very large d, it's almost as you are in a compressible flow, so you can afford different type of discontinuities, almost. And then you need to analyze. But what is difficult really is that you, when you try to build such solution, you need to deal with pressure. And pressure is a very non-local object. You want to describe some kind of a filament. If you want to show it as a solution, you need to get pressure everywhere. Well, Pfaffian of pressure, the matrix of second derivative. And I never were able to imagine a right combination of pressure derivatives. Yes? No, it's a space. I take it. No. Measurements are a snapshot. I take a snapshot. So I have a three-dimensional velocity field or vorticity field, right? So I take three-dimensional velocity field. It's a snapshot. There is no time here. No. You average over snapshots, but it's a static picture. So you take just point 1, you take point 2, you measure velocity here, you measure velocity here at the same moment of time. You take this into 12th power and average. It's straightforward. Just take half a year to get this data, and then you just average. Okay? So what I now did, I expressed to you the fact of breakdown of scale invariance in terms of structures. So you say, because we know in Burgers that there are shocks, and these shocks are rare fluctuation, but they produce contribution into velocity different moments, which are very different from the rest of the field, then it is this contribution which breaks scale invariance. Right? And now I want to give you a totally different view of this anomalous scaling, and this is something which is related to what we call statistical integrals of motion. This is an alternative. Well, it does not. This is an alternative viewpoint, and we generally cannot reconcile them. They kind of work for different things. So let's look at the same thing as we did from a Lagrangian perspective. Remember, this Richardson law was r squared behave like epsilon t cube, right? I would say that this is a diffusion, right? But kappa is itself as a function of time, of scales. So one may say that the Richardson law somehow tells you that this is a distance between 2 points, right? This is R12 Lagrangian. So you have 2 points. They start going out. And the further they are, this is R12 in time t, the more is their velocity difference. And we actually guessed naively that delta V behaves like R1/3. But it's a random process, so it's more kind of natural to describe it in terms of a scale-dependent diffusivity. So if we say that this kappa is proportional to R2/3 or to time squared, which is the same, then you would get this T cube. And it is this kind of a mental picture which were put into what Professor Vicol told you as a Kraichnan model. Because of course, these vortices, which we all understand what's going on. As you go farther and farther away, more and more vortices participate in separating these 2 points, right? Because if points are on this distance, the vortex of this scale do not separate them, right? But if they are on this scale, then this vortex already separates them. And these vortices are correlated. They aren't Brownian. But what the genius of Kraichnan was is that he realized that you can take a totally artificial time dependence. So you say that your velocity field in which your particle live is something which is wide in time, just fluctuate fast in time, but it's something which scales. So you, if you write a theta field, which is a marker, and it's just satisfies the equation without any forcing and dissipation like this, which is d theta dt plus v, and v is incompressible grad theta, you see this v is something that it's Gaussian, but it's, which means that its mean value is 0, and its second moment satisfy that it's delta correlated in time, and some function of distance. And you can pause here, because it's the second moment of velocity, you can say that this is R2/3, or you can consider anything else. And that immediately tells you that now you can write an equation for arbitrary moment of this quantity. So for example, you may write equation for theta 1, theta 2. It's pretty easy. So what you need to do, you just need to write here v1 grad 1 plus v2 grad 2 acting on theta 1, theta 2. You want theta 3, theta 4? Be my guest. Add here plus v3 grad 3 plus v4 grad 4. Now this is a random field, and you do average. Theta 1, theta 2, theta 3, theta 4. And now you know that when you average something with a Gaussian field, what you get as a result, you would get a diffusion equation, what already Professor Vicol shown you, but it will be with a diffusivity. So you would get sum from 1 to 4, because you have 4 coordinates, and you would have this I, grad I, and J, and where I put all the now, if you want to consider turbulence, You may add to this equation some forcing. You may add also diffusion. That would pump into it, this would dump into it. So what you would have here, you would have a correlation function of your f with theta, 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 etc. And that's a closed differential equation. And I'm getting old, so I cannot resist personal recollection. At 94, we were hiking with Krajgman at near Santa Fe. Huh? No, it was actually near Santa Fe. I remember. And I told him that I don't believe in all this anomalous scaling, all this absolutely wrong. This is just finite Reynolds number effect if we get really large books. And he was not immediately, and I was very young and very arrogant, and he was not immediately dismissive. He says that, you know, there must be something for which you can really check it. And he told me that, you know, that you can consider this. Of course, he did not call it Krajgman model, he called it white noise model, but I actually knew it because Kazantsev, I'm from Siberia, 1 year before Krajgman actually used this model for magnetic dynamo. So I already know that you can take velocity, take it white in time, and I wasn't very impressed. I thought that it's totally unphysical. But this is a closed equation. It's unbelievably ugly. Namely, you have 4 points. I mean, even in 2 dimensions, there are 6 coordinates, right? So it's an equation in a 6-dimensional space, etc. And of course, it always has what is called normal scaling solution, which you say that you look for steady state. So this is 0, and this you say that this is this operator. You say that what would be a scaling of this if I take scaling of pumping and divide by a scaling of this, and you get a normal scaling. But what Krajgman told me that he tried and tried and tried and failed to look for solution, namely this correlation function 1, 2, 3, 4, which turns it into 0. They do not need a scaling which somehow related to the force, right? They would be integrals of motion, right? If there would be no forcing, no nothing, ddt for such as we later started to call them 0 modes, they would be 0. And for some strange, since all, when I came back from Krajgman, I wasn't very much impressed by it, but then my student, PhD student at the time, Misha Cherkov, came to me and said that he derived the equation for which in Kazantsev model, he did not know Krajgman model, now it's called Krajgman model, the equation would be closed equation and probably it's solvable. And you know, and I always have this attitude that if your PhD student want to go some direction, go with him or with her. And then we found the solution. In a limit d goes to infinity. That's why I like this limit so much. And you find the solution, and its scaling depends on dimensionality and is not given by your naive power counting. And what it essentially tells you that there are quantities which are functions of positions of your particles. So there are particles which go away, and as they go away, they decorrelate. So you may consider some field, let's say theta 1, theta 2, theta 3, theta 4. Or let me tell you even better in terms of velocities. So imagine now I am jumping over all this story, and I am asking, what is this number? It's a little bit larger than 2/3. But what it tells us? Is something fundamental about it? What is this number that determines how fast the spectral energy of turbulence goes to 0, or how my spectral energy of turbulence scales with the distance, and it's not 2/3. And 15 years later, another PhD student of mine, Anna Frischmann, actually suggested a very kind of, we thought about it before, but she did it kind of in a very, very neat way, the explanation what it could be related. And it's again related to what we now call statistical integrals of motion. So imagine that you have 2 points, and there is a distance r12 between them, and it's a function of time. It's a Lagrangian approach. And there is a velocity v2, and there is a velocity v1. They're vectors, right? And now you let time run. And you ask what happened to v1 minus v2, and what happened to r12. Well, first of all, what happens to this difference with time on average? Let time run in Navier-Stokes equation or in your experiment. So what happens with time? Something like this, right? On average particle, there are some realization in which particles approach each other, but mostly if you start particularly inside in the inertial interval of turbulence, that on average your particle would separate. So what would happen to your velocity differences? It's grow, right? What happens to the average distance? Will also grow. I mean, don't hesitate. I mean, if I'm asking some question, doesn't mean that it's non-trivial question. I just want to wake you up.
Why does the velocity grow?
Because if you take a snapshot and you look at what is the velocity difference at this distance on average, and what is the velocity difference at this distance, that on average they are larger here, right? Huh? Well, on average, depending on which moments you would consider. So what I am now suggesting is, let me just check that I'm doing right notations. So what I am now saying, let's.
The difference between the velocities could be constant and still they're going away. So the question is like, so you're saying because in average they go away, then.
No. What I'm saying is the following thing, that if I look at the velocity of two particles, first of all, I have this, or I already erased it. No, I don't want to tell you this. I just want to finish the story. So what I'm actually saying is the following things. Let me take the modulus of this and ask if I can find such a function, it's dimensionless function, and take an average. How I do average? I average over all pairs which are at the beginning at the same distance. That's your address always asks, what is the average? The average is following. I take this pair, I take this pair, the distance is the same. I take that pair, okay? And then I let all this run, and I'm asking the following thing. Can I find such a G so that this would not depend on time? That would be what mathematicians call martingale. That would be what physicists like to call statistical conservation law. Okay? And now I'm saying that if it does not depend on time, at time equal to 0, this is just, I assume that g of 0 is 1. It's some constant, right? So this is just delta v squared, and I know that this is r naught in the power zeta 2. That's what experiment gives me. Now I want to relate this scaling exponent in the Eulerian average. This is just Eulerian average, right? I just average over all pairs which are at the distance r naught, right? And I am saying, okay, now let's time run to infinity. What I now want at time going to infinity is that I want that from this expression, this would have some asymptotics, right? And I want this asymptotics to be such that r naught disappears. It's an assumption. For Kraichnan model, I can prove this and compute such things. For example, for random vector transposed by Kraichnan velocity field. But generally, we just say that so what I would get is that my g as a function of its argument must behave as zeta minus 2 as its argument, okay? So in a sense, it tells me this very simple consideration. Tells me how these numbers are related to the scaling exponent of statistical integrals of motion. So what I'm doing when, and by the way, this G is not a power law everywhere. It's only power law at the asymptotics of time. Because incidentally, you can write, you remember this flux relation. But if you look from a Lagrangian viewpoint, what is written here is ddt of delta V squared. This is just a Lagrangian derivative of it, which tells you that your delta V squared initially as a function of time, and now Edris answering your question, how delta V, without multiplying by any function of R, what just happened on delta V squared as a function of time in short times. This is ddt at time equal to 0. It tells me that the ddt of it is minus 4 epsilon. And then you understand how difficult is three-dimensional turbulence. Is that in three-dimensional turbulence, epsilon is larger than 0. So your delta V squared starts from this quantity and goes down with a slope minus 4 epsilon. Incidentally, in 2D, this is 3D. In 2D, epsilon is negative and it goes up. But we all know what happens at very large time. At very large time, on average, delta V squared would grow because your particle would be more and more decorrelated. What this direct cascade tells you that even this second moment, its derivative. So the whole evolution, and I guess Alan Pomir probably did, probably tell you maybe more about it, but he did a very beautiful numerics about it. But it just tells you how non-trivial is the Lagrangian evolution. And the scaling of your second moment in Illyrian frame is related to this, to a very long time, asymptotics of your conservation law. Okay? And in this point, what we started to realize on doing all this Kraichman model first, but then hand waving about other things, is that a cascade fixes only this number. All this idea that you have a cascade tells you very little about a physical system. If you're an engineer, it's mostly all you need to know. But if you're a physicist, you are interested in the whole statistics. And all these numbers, they are scaling exponents of some very non-trivial statistical conservation laws which are related to the geometry. For passive scalar, geometry starts from 3 particle, 4 particle. But for velocity field, it already starts from 2 particles because those are vectors. And there is a geometry in between this V1 and this V2. As they go away, their direction decorrelate. And then their magnitudes also decorrelate. Okay? So essentially, and this is the alternative language in which we try to understand this anomalous scaling. So we related these numbers. Incidentally, passive scalar is something like this. It's, oh my God, it's in between on the same curve. Well, it's actually not, it's not passing through this third point, it passes through this point. Kind of, you know, yeah, but also close to, no, it's actually close to 2/3 and then goes like this. But all curves are convex. There is some kind of a mathematical condition which is called Hölder inequality, which tells you that this is the convex curve because they're averages of different moments. And there are two ways to understand these numbers. And burgers give you the simplest form, namely you identify the structures, the type of a local flow configuration which gives you contribution. And it could be that, so for velocity field, the asymptotic, the most singular structure gives you the highest moment. And if there is a most singular structure and no more singular, then all high moment would have the same scaling exponent, which is just proportional to the codimension of this singularity, or if you translate it into simple physical language, of what power of a distance is proportional the probability to find this singular object. If it's proportional to the power to the power 1, it means that dimensionality of it by 1 mentions the dimensionality of your space. It could be that this is non-integer number. It would tell you that your singularity is a fractal. So you have something, and it could be that it is like this. All these dreams that the most singular object in a flow is a vortex filament is just a dream. Because it's, for now, what Srinivasan has is like 2.06. Tomorrow they have better data, they would have 2.2. That's it. You are now looking for fractal singularity. Good luck with this. Okay? Now just give you 1 minute to relax before asking questions. Another historical remark, particularly related to the film Oppenheimer, if somebody already seen it. Krajgman graduated in 1949 from MIT and got to advanced study about the same time as Oppenheimer to work as Einstein assistant. And of course, what any decent person want to do when you work with Einstein, you want to do field theory, right? Einstein actually directed Krajgman to fluid mechanics. He says that, as you probably know, Einstein intensely disliked quantum mechanics in its stochastic aspect. He believed that the stochasticity and all such things must come from a natural classical dynamical aspect. And he was very much interested in the fluid mechanics, particularly in turbulence. And so he took this young guy, Krajgman, and said to him, you know, quantum schmantum, let's first understand how fluid flows. The idea, as Krajgman told me many years later, it was 1950, 52 probably. They thought like it takes two, three years. Look, I mean, they're great people. And Einstein was mostly known. So Krajgman was supposed to take care of fluid mechanics and then come back and say, okay, from fluid mechanics, we learned that classical nonlinear field behaves this way. Okay? And, well, 40 years later, when I've met him, and of course, when Einstein died in 1956, Oppenheimer immediately fired both Einstein assistant, one of whom was Krajgman, and another one was Bruce DeWitt, which I'm sure is absolutely. So two great scientists. That's why I personally dislike Oppenheimer, because Krajgman is my teacher. Anyways, that's historical anecdote which you may find interesting. So Einstein really understood back then at 50 how, and not only Einstein, for Neumann and Zager, many physicists, they really understood how interesting, strange is the flow of a fluid and how much effort you need. And for next 40 years, Krajgman was actually the face of theoretical physics, kind of trying to push it. And when Oppenheimer fired it, which I particularly hate, and Bob never told me this, his wife told me this, that he came to him and put a hand on his shoulder. And Bob knew, like everybody knew, that it means you're fired. But then he said to him things which I always hate to repeat. He said, Bob, it's really complicated problem, turbulence. Maybe you leave it to somebody better equipped to do it. And because for next at least 30 years, that's definitely, at least from a side of theoretical physics, but there were other great people, of course. But anyway, that's my view on Oppenheimer. Okay, so you are kind of waked up. Questions? Yes. Yes. So you, because you need this in some powers, this would compensate this power. This this is an assumption. I cannot prove it. Yeah. Well, yes. Or, I mean, no. Well, look, okay. First of all, I can do it for smooth flow as well. So there is nothing here which is, but for smooth flow, there would be trivial things, would be just normal integer power. I can do it for normal diffusion, which is a stochastic process, and then I know what are just harmonic polynomials, right? If you have a usual heat equation in multi-dimensional space, you have many particles which do diffusion. You ask, is there any combination of, let's say, 4 particle which does not depend of time? Be my guest. Take R12 squared minus R34 squared. This has kappa t, this has kappa t, they cancel each other, this is a martingale. You want to do it for force power, again, this is just harmonic polynomials. So it's trivial to build it. What is non-trivial here is, of course, this nonlinear dependence. So I don't think it's related to, what Kreitner understood, what was his genius, that non-smoothness of velocity make this convex curve in the scaling of stochastic conservation law, etc. Right? But they exist for general case. No, no, no. What I'm saying is that this stochastic conservation law exists for usual diffusion. I mean, this is the martingale for the diffusion, right? And I can build it r to the power 6, 12, blah, blah, blah. It's just 12th polynomial of this angular diffusion in angular space. What is this? It's just trivial. So I can immediately predict what is the scaling because this is just Laplacian in multidimensional space, and I know what are the scaling. What is non-trivial here is that they are exactly like them, and what Gavetsky and Kupianin did exactly the limit when this is close to this is you can compute perturbatively from there. So this is what is more important is that this spontaneous stochasticity is important not about the existence of conservation law, but of their non-trivial scaling. That this thing is a convex curve. That's where this comes from. Yeah. Well, this definitely non-smooth. If you are smooth, you always remember your initial. In this sense, you're right. But in the usual diffusion, I am already non-smooth. I forget the initial. Well, I do not forget. I mean, this is r naught squared plus kappa t, and this is r naught minus r naught squared plus kappa t, right? So this is, of course, I do remember here too, but when this is getting very large, I forget it. But what is interesting and important is that non-smoothness produce as an effectively as if my particle interact. So the cloud of particles, this multi-particle statistics, is as if they know about each other because velocity is correlated. It decorrelates, but not fast enough. Diffusion means that all the velocities are totally decorrelated. This is not diffusion. It has diffusivity scale dependent. Tells you that the velocity is actually correlated. And this imposes a non-trivial correlation between particles. More questions? Yes. It's not neuter in any way, right? So I don't have Hamiltonian. I cannot relate my conservation law to the symmetry. It's a martingale. In a sense, for me, mentally, it's always compensating growth of something by the growth of something else. So in a sense, when I do passive scalar and I see this kind of multi-point strange scaling, I say, okay, that there is a kind of particle go away, but then their angles are getting kind of decorrelated. Their directions are getting decorrelated. And as in this case, you see that you compensate growth of this by the decay of this. And that on average, it's a martingale. And it's dependent on space dimensionality. It's a very, very non-trivial thing. And I don't have a good intuition about it. Thanks to Kreitner, we can compute something, but that's it. Yes? That's what.
Could they make also shocks, or can you take them out from your consideration that you say it is only the filamentary structure?
If I would see this exponent goes to the 3, then I would say that the condimension of my singular object is 0. It's a point, like stagnation point. Then I.
Stagnation points are typically the accumulations of pressure that they are, because they are coming together, they are
If something turns into sheets, then it would give me a scaling 1. And if I already passed the scaling 1, it means that's not my most singular object. So for now, as long as the great people of NYU reach 12th moment and give us number 2, we believe that most singular objects are linear. In 10 years from now, they would improve the data and it would be 1.5 or 2.8, and then they start speculating again. But at the moment, it's like this, right? We just read what are the object by this asymptote. Yes?
I would personally be very careful with this estimate, because what is C really is a large deviation function.
You're right.
I mean, the Paris interpretation is codimension, it's nice, etc. But the real mathematics,
You're absolutely right. I'm substituting asymptotic reasoning to a very real Reynolds number, real finite statistic data. But what can I do? That's what the data I have.
It is
Yes.
a very naive question, but if that is the case, that it would be produced by these filaments.
Yeah.
Why are they not able to visualize them in their?
Oh, it's probably just another half a year of work. I mean, they're working on it. So, but it's, computer, it's made of iron and people are not. So if you have program running, it just gives you a moments. But then you need to write a new program which would do a conditional averaging. Every time you see a large value of this, show me the flow configuration. And it's crazy, this flow configurations. You need to look by your eyes, and every one of them say, okay, now I want to sort them like this and put them one on another. It's a very non-trivial analysis. Okay? Well, you can do it, but at some point somebody does. Yeah. Yes?
You mentioned that quantum field theories are effectively theories, which to me means that they are valid on a certain energy scale.
Yes.
Did I understand it right that the introduction of the cascade and the related intermittency makes these theories valid on all energy scales or time and length scales?
No, it means that we go opposite way. So quantum field theory, we used, when I was a kid, when I was a student like you, we were talking about elementary particles. There is no elementary particles. There are just fields and their excitation. And what we all do, I mean, when we're doing condensed matter, quantum field theory, etc., we do build effective theories which work at a larger scale than whatever microscopics is there, right? We say, okay, there is something, but anyway, whatever we see is just excitations running on some kind of, we don't talk about quarks and gluons. This is proton, this is neutron. We don't look inside. And in our case, it's totally, which means that there is something at small scales, and we try to describe at larger scales at lower energies. And we don't know what is at Planck scale, right? That's essentially. Now, in turbulence, it's different, particularly in direct cascade. We'll talk in 3 hours, we talk about inverse cascade. But we say we have a forcing, it determines everything. The way we steer the fluid, it determines everything, plus equation of motion. Okay? So now we want to understand what happens at scales much, much smaller than this scale as we go down the cascade. And what I told you today is that you cannot forget how many steps you passed. So it is this scaling, this delta, which always have this L over R in the power delta. This is the number of steps that you pass until a given scale R from your forcing scale L. So what it tells you is that your turbulence remembers how many steps you passed. And that's what makes it so different from quantum field theory. But in some cases, you can perturbatively try to compute such things. Well-earned break.